So last time I was starting to do character theory. Okay. Remember we had characters chi alpha of irreducible characters is just trace of the irreducible representation G. It's a function on the group, okay, which is a class function, that is chi alpha H G H inverse. Right? We have seen this. Yeah? They have orthogonality relations. They are well, we know that chi alpha G bar is chi alpha G inverse. We proved character orthogonality, that is summation G chi alpha bar of G chi beta of G is order of the group times delta alpha beta. We proved that, no? Then we also proved that the character of a representation chi gamma completely identifies it. Up to equivalence. Great, we have three. We should celebrate the riches, right? Okay, great. Okay, please feel free to ask. We are only three, so you can think of it as some private tuition. Okay, there is no problem. So this is what we proved last time. இந்த வர்தன் எங்கேப்பா? இன்னும் தப்பு போட்டிருக்காங்க, யூடியூப்ல இன்னும் தப்பு போட்டிருக்காங்க. சரி, okay. Now today, and then I also started discussing a particular representation of a finite group, okay, namely the left regular representation. We will see that this is very, very important. Okay. By the way, this is also in my other lectures I was using this GNS construction and so on. This is what is used, this is the starting point of those activities. Okay. It's very simple actually. First you take this, and goes back to 19th century, you take this G, okay, consists of elements G alpha. I am thinking of the discrete case. Okay. Then you construct the the group algebra which simply consists of all linear combinations of the group elements, where the psi alphas are in complex numbers. Okay, and their product is, if I take the algebra is a vector space with this as basis, you declare them to be independent. Okay, you consider the vector space what is all freely generated by these elements. You can take any collection of things and make a vector space. Okay, say they are linearly independent and take formal linear combinations. Okay, so it is that vector space, but there is a natural product here. This will be psi alpha eta beta times G alpha G beta, right. So this is some element of, this is some element of group. So this is in the group algebra again. Okay. So this is your group algebra. Algebra has a product So this is the product. Now what you do is, okay, the following: to each G, each element, okay, let's say each G alpha, let's say, associate, let me do as I have done, a vector G alpha. So I introduce a vector space, and naturally again I define this thing to be psi alpha times summation G alpha. So I explicitly make that vector space and introduce kets for these elements, and I write like this. Okay, these are linearly independent by definition. Now I take any element of the group, to each, say G alpha and G, okay, define a linear operator I want to call this, okay, on the vector space, and probably need some vector space. Let me call it is actually V, okay, let me call it as this vector space. I am going to define for each element in the group a linear operator on this vector space, okay, by T of say S acting on a vector psi alpha G alpha is defined in a natural way. Okay, this is psi alpha times summation S G alpha. Sorry?
This is essentially what GNS does.
This is the this is exactly the GNS. This is a regular representation for groups, okay, but obviously it will extend to the group algebra. Okay, so this is the starting point of the GNS construction. Exactly. This is how they Nymark started it. I have not seen the papers on Nymark, but I am told that is how it came. You define like this. So this is also the regular representation. This is the this is a left regular representation. I had given it previously in terms of functions on a group. Okay, here I am giving it in a slightly different language. Show this is equivalent to 1 on functions. Remember, it had defined another thing, T hat of S alpha at a G is alpha at G inverse S, right. I had defined previously like this. Remember that I had defined the left regular representation, but this is the same, well, up to equivalence these are the same. In other words, if you choose your basis cleverly, here you can show that the action of this on this basis is the same as the action here. Okay, so the basis is almost obvious. You define, I will give you a hint, choose a basis like f alpha at g beta as delta alpha beta. To take this basis, that is a collection of points, no? This group is a collection of points. So I can choose a basis f alpha which at the point g beta is 1 and 0 elsewhere. Okay. In that base, so this f alpha will correspond exactly to these g alphas. the way the matrices or the representations act, they will be identical. Okay. This is a good exercise to try, okay, to show that this is no different from that. Say again. Basis, dual basis. Yes, exactly that. That's correct. There is a duality F, yes. This is exact, but in this case the two representations are equivalent. You don't get anything new. Good point. Okay. Now I want to see the miracle of this regular representation is the following. Okay. So this group miracle is the following. Okay. Consider the matrix of say Ts, okay, in basis, this basis is, let me compute it. Its computation is Ts G alpha is equal to G by definition. Okay. The definition S G beta times d beta alpha of S. This is a definition, but this is equal to S G alpha. Yes, maybe I should label the matrix elements. Yeah. So this is some G alpha prime. What is a better way to write? It's better even to label this by d of G beta G alpha, summation G beta, and then write this as S G beta. S G alpha. Okay, I label the matrix elements by the group elements instead of numbering. It's easier to see what is happening. This is S G alpha. Okay, so you see immediately that how did you go? This is I am getting confused. This has to be one second, I am just getting confused. Yeah, this has to be, so this is 0, so d G beta G alpha, or this of S, okay, is 0 if in the sum here I must get S G alpha. So if G beta is not equal to S G alpha, okay. Yes, I am summing here. No, I can say it nicely. I am trying to compute these matrix elements. It is non-zero. There is only one non-zero element. When I am going over all G beta, this must coincide with this. So this is 0 unless G beta is not equal to S G alpha. This is 0. Okay, and 1 and d S G alpha G alpha of S is 1, right. So but this 1 is on diagonal if only if, right, it is a diagonal means SG alpha is G alpha. This has to be so, or S equal to identity. So the diagonal, so only then, okay, D, okay, G alpha identity is 1. Otherwise it is 0. Wait. Yeah, okay.
You can use this to recover your completeness relation.
From here, no. I am going to recover something more striking. Here, what happens is that this matrix is 1, 1, 1, 1 as you expect. All the other matrices have off diagonal entries. Okay. So, if we take the trace, so character of S is 0, S is not equal to identity, is equal to n if S is equal to identity. This is a very important result. Okay. Okay. So, consider the writing, okay. So consider, okay. So if say chi of S is summation f alpha chi alpha of S, f alpha is the multiplicity of the irreducible representation alpha in this, then I can compute it, no? This is a situation here. So I multiply by chi alpha bar 1 over n. So I write f alpha is 1 over n chi alpha bar of S and summation S times chi of S this is orthogonality, but this is the normalization. So this is 1 over n, but this is all 0 unless this is identity. But with this identity you get n here, okay, here, and this is chi alpha bar of identity. But what is chi alpha bar of identity? It's a trace of the unit matrix in the representation given by alpha. So that is equal to sigma alpha, which is dimension of IRR alpha. Okay. So what have you discovered? The number of times the irreducible representation alpha occurs in the regular representation is equal to its dimension. Okay. So we get this incredible result. Okay. So number of times n IRR of dimension IRR alpha of dimension sigma alpha occurs, okay, in regular representation is equal to sigma alpha. Yeah? So each IRR occurs in the regular representation. One lesson you get is, so each IRR actually occurs in regular representation. It is some kind of a master representation from which you can get everything. In fact, there is a each one occurs so many times, okay, depending on the dimension. Okay, it's so far as I know, not is an open problem. Gelfand proposed a problem. He called some representation a model representation, where each irreducible occurs only once, okay, not so many times. And he called it a model representation. It is a representation theoretically useful thing. And to my knowledge, it is not known. Some answers I think are known, but people doing quantum information theory seem interested in this, and people like Subhash Chaturvedi and Mukunda here probably are interested in that. Okay, but to my knowledge, it is not solved. Okay. Now from here, so by fooling around with regular representation, I can find all irreducibles. This is one lesson. Okay. This is the reason why all this activity, GNS and so on, start from here, because it is some kind of a master copy from where you can get everything. Okay. Now let me do another thing. Okay. So write V as the orthogonal direct sum V, okay, as direct sum, okay, it will be V sigma alpha. Okay. Well, for alpha you will get V alpha. This will be sigma alpha terms. Okay. Then you will sum over the different things. A group like that. Okay. There are sigma alpha copies here. Then another one, maybe another. So let us see what happens. So in this basis, okay, this matrix DS will be some huge matrix. Okay. It will have D1, okay, sigma 1 times, right, then it will have D2 sigma 2 times and so on. Okay. But what is the total length? It is acting on the group algebra. So what is the total length here? Order of the group is n. Right? So you get a sum rule. What is the sum rule? By comparison. This is one of the most important sum rules. N equal to what? Sum of sigma alpha squared. Right? Each sigma alpha occurs sigma alpha times. This is sigma 1 squared, right? Plus sigma 2 squared plus sigma 3 squared. So you get this rule, where the number of terms, okay, alpha, okay, is over classes, conjugacy classes. You don't have to go on summing. Okay. There are only distinct irreducible representations corresponding to the number of conjugacy classes. So the number of, you write this, okay, for each conjugacy class you associate one sigma alpha and write this equation. So it's a Diophantine type equation, all are integers. So you have to solve this equation. There is another theorem which I don't know how to prove. Okay. Also, this is this proof is given. sigma alpha divides n. I will put a question mark, exclamation mark. This is a theorem. You can see, I did not know this. Barry Simon's book. Actually, Barry Simon has written a book on representation theory of finite groups, which is available again. Okay? You can download it. Okay? And it's actually, his presentation is closely following mine. It was not intentional. I have discovered this book by trying to chase a theorem that we have not proved. Okay? And there this result is quoted and proved, and he says that this is one of the astonishing results which have been proved, and it is something like, he says, I don't know, he quotes it, a story from Pythagoras. Apparently Pythagoras discovered at some point that square root of 2 was irrational, and so he became so unhappy at the imperfection of integers that he committed suicide. I don't know what is the meaning of this quotation in Barry Simon, but he gives it this quotation. I don't think the proof is horrible, but he says it uses results from algebraic number theory and so on. I would like to read it, the proof, but I don't know. I didn't know this result until 3 days ago. 3, 4.
Looks a bit like Lagrange's theorem.
Huh? No, but it is a dimension of the Lagrange says that the order of a subgroup divides the order of the group. Here the order of the irreducible representation of a group divides the order of the group. It is a different statement. Okay. Okay. The other one, Lagrange, is easy. This is a it's not too difficult. Okay. But I will also say, let me say, if there is interest, I will show you. Okay. Here we can prove, we now have all the equipment that, okay, number of, this we never proved, number of classes, conjugacy classes is less than or equal to number of different distinct IRS. We have enough equipment to prove, I mean the way it is proved, I mean I left it, I said I didn't know the proof. I know the proof now. Okay. She supplied me the proof and it appears to be given in the book Maths, Fulton and Harris, some book. Okay. But the proof is not difficult, but I will keep it aside to save time. It will take half an hour, so let me go on. Okay. But you may want to get the notes from her. It is a couple of pages in her notes, and I have also wrote down notes. It is not difficult and uses the fact that in the regular representation every representation occurs, every irreducible occurs. That is all that is really needed. Okay. Then you have to do this Schur lemma activities. Okay. You have to make some masala with Schur's lemma and give the answer. Okay. It's amazing, no? Because I have not. I have used only general properties of the group, okay, and all these things are tumbling, okay, out. I have not even told you which group I am talking about. So let me see how it works. Okay. Example 1. Let me take S2. Okay. Here, okay, there are two classes. Okay. One. E, okay, class containing E. Let me write like this. So the class containing the identity and class containing the transposition. There are two classes, right? The order of the group is 2. See, so order of the group is 2. So it is sigma 1 squared plus sigma 2 squared. There is only one solution which are all integers. So sigma 1 is equal to 1 and sigma 2 equal to 1. So there are only two irreducible representations. Okay. In one, okay, so we have two IRRs. That's all we have. In one, what are they? I mean, you should be able to guess the irreducibles. They are both one dimensional. One is everything goes to identity. Okay. So both these elements, okay, E and 1 2 2 1 go to identity. The other, what happens? You can guess. The square of this is this. So this can go to 1 or this can go to what? -1. This is the anti-symmetric representation. This is symmetric representation. Okay. In the other, okay. Let me also look one more. Okay. Let me look at S3. Okay. Okay. There are three classes. See later. Let me see. I'll prove what are the classes. Class 1, okay, is simply the class containing the identity. Okay. Say class 2, okay, all transpositions. So there are the form Ij, Ji, Kk. So they just permute two of them. And class 3 is cyclic permutation. Okay. Namely 1 2 2 3 3 1 and all the cyclic permutations. Okay. I have to show it to you, but I will show it momentarily, but just to see how these things go. So we find some rule. We know the order of the group is 6. There are 3 classes. So write this equation: sigma 1 square plus sigma 2 square plus sigma 3 squared. I use both those results. 1 2 3 divide 6. But 3 is no good. Okay, 3 as 3 squared is 9. Okay, it is out as a sigma. So I have only 1 and 2. So what is this? There is only one solution with 1 and 2. What? Sigma 1 is equal to sigma 2 equal to 1 and sigma 2 equal to 2. Huh? Sigma 3. There is no other solution. So these two are what the analog of this. The even here sigma 1 is identity representation. These are one dimensional representations. So in sigma 1, okay, so the IRRs, the 1D IRR, okay, so IRRs, okay, one is trivial, A, trivial one, all elements go to 1. Second is all transpositions go to -1. Okay. Okay. And since we will prove, then this will fix all the things. By homomorphism, any representation will show that any element of the group is a product of transpositions. So everything is either an even transposition or an odd one, odd number of even or odd. All even elements of the group go to 1, all odd elements of S3 go to 1. Third is more complicated. See later. That is a two-dimensional representation. Okay. How do I represent permutations on 3 objects as a two-dimensional representation? It's not trivial. Okay. So that requires some more study of how the stuff fit in here.
The sum rule can, I mean, for large n, can be fairly difficult to.
For large n, how it goes? Okay, this is the one of the famous Hardy-Ramanujam problems. Okay, what happens for the? We'll show now. Yeah, this is one of the famous things that Hardy and Ramanujan did. Okay, we will see momentarily that for the permutation group, okay, the number of conjugacy classes is given by partitions of n, okay, where lambda I are partitions, right? Lambda 1 up to whatever, okay. Lambda I integers, their sum is 1 n. We will see this. Okay. So this is not difficult to prove. I will show it to you. Okay. Then you can ask how many partitions of integers are there. Okay. And for large n, how do you do it? Okay. This is a problem which was solved. The asymptotic series for these partitions is the work of one of the Hardy-Ramanujan identities in number theory, okay. And it has been extensively used both in string theory and in statistical mechanics. Okay. It is highly non-trivial. Okay. I mean, if you try to prove it in cold blood, is quite difficult. Okay. So, but they proved it, and it is how to improve it. Can you get better formulae? All these things are open issues. So we will see how it goes. Okay. Okay. Now I will now specialize. So the general case I don't know. Okay. You are asking what do I know about for large n? What do you mean by large n?
No, I mean, as n grows larger, number of ways, I mean, whether or not solutions to that equation exist, you know.
They will always exist, because any finite group has an irreducible representation, has a representation, right? Any finite group, because it has a regular representation, and it is unitary, because I gave you the, so it can be completely reduced. So every finite group has a complete system of irreducible representations. Okay, there is no doubt about that. Okay. Then if you ask more subtle questions about how it divides, how many terms there are, this I do not know, but some results are known. Yesterday that guy Anil was holding forth on that, okay, on similar problems. Okay. There are apparently results, I don't know those things. Okay. So now we want to look at the symmetric or permutation group. Sn. This is the only finite group I will discuss, because somehow it contains information on all possible finite groups, because every finite group is a subgroup of Sn, and also it is not possible to go group by group. Okay. For each finite group, people start using special techniques to find representations. Okay. There is no universal way of, some things would have some simple properties, you use that. No? So there are tables of characters in crystallographic finite groups. There are tables. Okay. If you look in people doing crystallography, they will give you tables of characters, so you can work with that. Okay. But I will only show you how this goes. Okay. Now we know the notation here, and now I want to show you. Okay. This one. Remember, okay, recall. If G is 1G1, NGN is an Sn, the inverse is G11 up to GNN. This is useful to know. Now I want to tell you, and this is an important concept, okay, that a cycle is what I will copy from here. A cycle, okay, of length n, length k, okay, a cycle Z, okay, is an element with Z to the k is equal to identity, okay, and k is the least such integer, k being the least such integer. Positive integer. Okay. For example, for k equal to 2, cycle of length k equal to 2, the cycle is a transposition. Okay. These are transpositions. Okay. It will be of the form, say, other form, say 1, 1, 2, 2, etc. Then you have I, j, j, k. Okay. I, j, j, I. Okay. We write this as Ij. Understanding that the rest are not touched. Okay. Similarly, k equal to 3, they will be of the form I, j, k. Of course, I not equal to j, not equal to k. It's not I, j, k distinct. And then it doesn't do anything for the remaining ones. Okay. So this is a cyclic permutation on 3 objects, and the rest it doesn't do anything. Okay. So this is a cycle. Then the statement is the following: okay. Any S in Sn is a product of cycles the decomposition, okay, is unique, okay, if no two cycle have common elements okay, and we don't put in unary, we don't put in unaries like 1. Let me see whether I want I should not say like that. I should, this is wrong statement. Okay, I have no common elements. Okay, provided this is correct. The total number of entries is n. So you do put in. I am sorry. So you add in. If there are unaries, you put in the unity, but you should exhaust all the integers coming up to n. If I omit this, then there is some problem when I try to do diagrammatic things. Okay. How do I prove it? So let me prove it now. Okay. For given S is equal to 1 S1 n Sn, okay, what do you do? Start from 1, yeah, it goes to S1, right? S1 goes into whatever it is, SS1, and then finally it will come back here. Okay, this is one cycle. Take it out. So you remove these things. Repeat the process. Okay, so you can decompose the whole thing into cycles like this. Okay, so I have okay, any S can be decomposed into a set of cycles. Then what I did was the following. Okay. So this is okay. So if there are alpha 1 cycles of length 1, right, alpha 2 cycles of length 2, etc. Let's say alpha n cycles of length n. Okay, what I can say is n is summation I alpha I. The sum I take here, right, alpha 1 cycles are length 1, alpha 2 cycles are length 2, alpha n cycles are length n. Okay. So when I add them up, I should get back n, because I am dividing n entries. Okay. So this is surely true, right, because the sum of the elements should add up to n, right. Now I do the following, and then I will show why this is so important. Set lambda 1, which is alpha 1 plus alpha 2 plus etc. plus alpha n, lambda 2, which will be alpha 2 plus etc. plus alpha n, lambda 3 will start from alpha 3 plus etc., and lambda n will be alpha n. Add them up, then okay, a summation lambda I is summation I alpha I, which is n, then you get b lambda 1 is larger than or equal to lambda 2 is larger than or equal to lambda n. So the lambdas characterize the cycle structure of a permutation. So this is this set here by definition, okay, is a partition of n. So every cycle, the cycle structure of a cycle of a permutation is given by the partition of n, okay, right. The cycle structure of a permutation is given by a partition of n. Let me show they are represented by a Young diagram. Okay. The diagram is written lambda 1 boxes, okay. Then you have lambda 2 boxes, etc., okay, some lambda k boxes, and the remaining entries are 0, you don't put anything there. So this is nothing is inside the boxes right now, they are empty boxes, okay. We will fill them in later. So the entry box is a Young diagram. You cannot have a row here bigger than the previous row, that is not allowed. It is the allowed Young diagram, the rows either stay the same in length or decrease in size, okay, until they we have come now that the cycle structure is given by Young diagrams. Why is it so important? The importance is that, okay, a conjugacy class, well, you can write it as a theorem. A conjugacy class in Sn is given by consists of elements of the same cycle structure. That is, they are characterized number of cycles. So the conjugacy class given by the cycle structure, okay, that is by the partitions of n. They are labeled this I have to prove by partitions of n. So the number of irreducible representations of Sn are given by partitions of n. Okay. So this I have to prove, this is easy. So number of IRRs of Sn are given, is given by partitions of n of integer n. So this has to be proved, it is not difficult. Astonishingly, you will see that the proof of this result is easy. Okay. What is more subtle is, if you give me Young diagram, we know it is associated to some irreducible representation. So you can ask, what is the dimension of this irreducible representation? Okay. I give you a diagram like this. Ask, what is the dimension of the irreducible representation, and how do I find the matrices explicitly? That is a different story. It is not easy. Okay. Of course, now people know a lot. Okay. For Sn, let me remember, there is something called hook rule, which I will try for. First, let me check it. And if my memory is correct, I will give it to you. Okay. Jean knows. Okay. Then finding the matrices, there are all these allowed diagram, allowed tableau, and some activities you have to do, and you will get the answer. So I will describe the procedure to you completely, so that you can go home and do the calculations, but I will not give the proofs. Okay. If you want the proofs, the most detailed considerations are in this book of Werner. I suspect that it is also in Barry Simon's book. I have not checked it. Werner definitely has it. He has explicit formulae for the matrices in some factorials and so on. He gives the answers and he describes the proofs. Okay. So that tomorrow what I will do therefore is to show this result. Okay. Then I will discuss the permutation group representations in full. Okay. That is how to find, how to construct the representation explicitly. They are of importance in considering particle statistics. Okay. For example, parastatistics, bosons, fermions, paraparticles, what they call braid statistics, they come. Okay. So it's good to be aware of it. Okay. So I will tell you how it works. Then I will probably pass on to Lie groups. I think the only thing I would like to have done is this proof that the number of cycles is less than or equal to number of classes. It's quite an elegant proof, but it takes a little time, so I'll skip it.